Okay, so this is the last theorem we discussed, the term-by-term differentiation. I just want to make a small remark here. So the theorem only tells you that the series corresponding to the derivative has the same radius of convergence. However, it doesn't tell you what's going to happen at the endpoints. Okay? So what's going to happen, and I'm not going to prove it, you could lose convergence at the endpoints. It could happen that the original series converges at, let's say, minus r, and the series corresponding to f prime does not. Okay, so that's just a remark. Okay. Okay, our next theorem is going to be called term-by-term. I'm going to be a bit lazy. Term-by-term integration. Term-by-term integration. So we start with a series converging to a function on some interval which is not just the point 0, so r is positive. Then for any x less than r, now instead of looking at the derivative, I want to take the integral. So I'm erasing this. So this remains the same. Write it down. And now I want to do the following. I want to ask, what is the integral, let's say, from 0 to x of f? Okay, the integral from 0 to x of f. So I'm integrating in the definite sense. And, well, obviously, it's the integral of this thing, right? Maybe I shouldn't write f of x because I'm integrating up to x. So let's, yeah, we can leave it like this. Yeah, we can write f of t dt to be more accurate. So that's the same as integrating this with a t here from 0 to x. But the theorem tells you integrating the sigma equals sigma the integrals. You can change the order. First integrate, then sum. And integrating x to the n, or integrating t to the n, is what? Let's do a little side calculation here. What's the integral from 0 to x of t to the n dt? Right, it's t to the n plus 1 over n plus 1, evaluated between 0 and x. Right? This is Newton-Leibniz. When you plug in 0, you get 0. When you plug in x, you get x to the n plus 1 over n plus 1. So this is a little side calculation. And that justifies writing here sum n equals 0 to infinity, a n integral of x of t to the n, which is x to the power n plus 1 over n plus 1. Clear? I'm integrating term by term, integrating each power separately. Clear?
Why did you switch the variable to t?
Because I don't want to write integral from 0 to x of f of x. We discussed that when we discussed this thing originally and said it's supposed to help confusion, but sometimes it causes confusion. And I hope by now you're over that, but apparently some of you are not. Same radius of convergence. Good? We'll do an example or two in a second. Okay, so this is term by term integration. And let me just make a remark. In fact, this remark is relevant to the previous theorem as well. Why is it not trivial? Why are these theorems not just duh? What am I doing? Instead of integrating the sum, I'm summing the integrals. We know that. We know that the sum of integrals equals the integral of the sum, right? Why is this not a trivial statement? Answer. We know that the integral of f plus g integral equals the integral of f plus the integral of g for finite sums. This is an infinite sum. So we don't know it. And why is it tricky? Because what's going on when you try to put this into a snake, when you want to snake a sigma, what you're doing is taking two limits. The snake is a limit. It's a limit of Riemann sums, remember? The sigma is a limit. It's a limit of the partial sums. That's how series were defined, right? So there are two limits going on. They're in the background because we don't do it like that, but they're in the background. There's the limit of the Riemann sums and the limit of the partial sums defining the series. And what we want to do is interchange those limit processes. First take the limit of the Riemann sums for this, then sum up, then take the limit of the partial sums. And in general, interchanging limits is illegal. It's usually false. And you'll see that a lot in Calc 2, when there are functions of several variables, and it's very tempting to change limits there, but you can't do it. Okay? So here, it's a particular case, and that's why it's a theorem, and that there's a big machinery in the background, which we're not discussing, that allows this, the machinery of general function series, which I mentioned earlier, that says that this is true in this particular case. Likewise for derivatives. Changing the order of summation and differentiation is also a limit process, right? What's the derivative? It's the limit as h goes to 0, f of x plus h. Remember? It's also a limit. So changing order of limits, in general, false. In these two theorems, very special case, true. Let's do examples of this. So here's another example. Let's call it example 3. So we know that 1 over 1 minus x equals sigma x to the n. This we know. And this was true for any x less than 1. So before I actually do term-by-term integration, I want to do a little trick. Okay? Do you agree that if I write instead of x, let's say t, it would still be true providing I write the t here and here? Do you agree? Yeah. Would it be true for any t?
No, absolute value of t less than 1.
Right, only if t satisfies this requirement. Do you agree? What if I put here s, and here s, and s is less than 1? Is it true? Yeah. What if I want to put here t squared? Can I do that?
The absolute value needs to be smaller than the square root of 1.
So I can put here whatever I want, a number, a variable. I can call it whatever I want, providing it's in the domain of convergence. So if I want to put here a t squared, so for example, if I want to write 1 over 1 minus t squared, this equals the sum, n equals 0 to infinity, of t squared to the power n, or t to the power 2n, providing what?
T squared less than value.
Right, providing t squared is less than 1. But when is t squared less than 1? Only if t is less than 1. Do you agree to this fact? Everybody? So there's no mystery going on here. It's just, you can plug in anything providing it's less than 1. So I want to plug in, by the way, here's another power series that we know, right? We just found a power series for a different function. But that's not what I want. I want to plug in, not t squared, I want to plug in minus t squared. Can I do that? Providing what? Right. So if I plug in minus t squared, I get 1 minus t squared, or 1 plus t squared. And that equals, plug in minus t squared here. What's minus t squared to the power n? Let's write it. So this equals sum n equals 0 to infinity. I'm going to throw out the minus 1 to the n, and then t to the power 2n. Do you agree?
Can you do it with arctan?
That's where I'm heading. You're still a step ahead of me. Good. Very good. So for which t's is this correct? This is correct providing minus t squared is less than 1. But minus t squared in absolute value is less than 1. Only if t squared in absolute value is less than 1. Which is only if t in absolute value is less than 1. Did everybody follow? Does everybody agree? Questions? Good? Okay, and now we had a magic suggestion here from the audience. Let's integrate this. This is the derivative of what? Arctan. So let's integrate this. So the integral from 0 to x of 1 over 1 plus t squared dt. On the one hand, this is just arctan of t evaluated between 0 and x. I'm doing math like in Hebrew now because that way I want to do the other direction. Do you agree to this? And what is this? This is just arctan of x. Does everybody agree so far? On the other hand, when I integrate this, that's the same as integrating the series, or integrating the series. How do I integrate a series? Term by term. So what do I get? So here I'm using the theorem, the term by term integration theorem. What do I get? I get sigma n equals 0 to infinity negative 1 to the power n. I just left this untouched. And then I want to integrate this term by term. So what's the integral of t to the 2n? Right, t to the 2n plus 1 over 2n plus 1. And then I need to plug in the 0 and the x. So it's t to the 2n plus 1 over 2n plus 1 evaluated between 0 and x.
Isn't it n equals 1?
I'm integrating. I'm going up 1. So this equals, so when I plug in 0, it's 0 again. So when I plug in x, what I get is sigma n equals 0 to infinity negative 1 to the n divided by 2n plus 1 times x to the power 2n plus 1. And the conclusion is that this is the power series for arctan of x. We just found it. So this equals this equals this equals this equals this. So they equal. Clear? So here we found again, and note several things that go on here, and it's important to pay attention. As I said, this topic really, everything we did in the course kind of comes together. So the first thing to notice is that when you write them in sigma notation, they look similar to one another. Note that this looks almost like sine x, except for the minor difference that there's no factorial here. And that's not a minor difference. It gives you a totally different function. Do you see that? Everybody? That's one thing to notice. Another thing to notice is that when you take a function, if I were to ask you, what is the power series of arctan of x? So the tools you have at hand, you kind of have to think, how would I work with them? So what do I know about arctan? Well, I know its derivative. I know this is the derivative of arctan, or with an x. So if I can find the series corresponding to its derivative, I can integrate it and find arctan. And then you have to think, okay, what does this resemble most of all? And say, hey, this kind of resembles this. Right? So, okay, how do I get from here to here? I plug in a minus 2 squared. So that's how, minus t squared. So that's how I get this, and then I integrate and I get this. So there's a lot of, you need to be creative. You need to kind of try out things, think of things, but the more of them you do, you get used to them. Okay? So you need to recognize things you know and use them. Okay? Just a small remark here. Note that, so remark, the original series we started with was the geometric series, 1 over 1 minus x, converges only for x less than 1, right? Arctan, verify, it's very easy, verify, arctan x, which is that power series that we just found, converges, the power series for arctan x converges on the closed interval, I think. Yeah, converges in x less than or equal, converges 4. So when you integrate, again, the radius remains the same. R is 1. But when you integrate, you may gain convergence at the endpoints. And this is what happens here. So the one you started with only converged on the open interval. After integrating, you get convergence at the endpoints as well. Okay? And the opposite phenomena for differentiation. You might lose convergence at the endpoints. Yes?
This seems to me like a major, I don't know, disadvantage of the Taylor series that the domain is so shrink. Like if you have just such a small domain. I mean, if we just look at arctan, the domain is like negative infinity infinity. And
the approximation process using Taylor series is hiding the fact that you're trying to approximate a very general function using a polynomial. That's where your hands are tied. So arctan looks something like this, right? You want to find a polynomial that is near arctan, that approximates arctan, a polynomial, or of higher and higher and higher degrees. But still, the phenomenon of having, just one root and then being bounded, that's not a polynomial. That's not a polynomial-like kind of...
a polynomial that has an infinite degree, I could expect it, I think.
Well, it doesn't work. It doesn't work. So you're right. You're right. Arctan, the power series corresponding, although arctan is defined on the entire real line, the power series, when you get around 0, you can do it around any number, but when you do it around 0, you only get a power series which is valid between -1 and 1.
But R stays the same also if we do it around 20, for example, it will be just from 90 to 21, right?
No, it would be a different power series because it would be not given in powers of x to the n, it would be given in powers of x minus 20 to the n, right? It would look completely different. Okay.
Question
Yes.
on the endpoints. We said that when we're talking about differentiating, we can lose.
Right. Right. It's only a remark. It's a side feature of this business, but I just mentioned
on
it.
the case that is diverging on the two of them, we don't need to check the endpoints because we don't have anything to lose on the derivative side.
Right. Right. Exactly. So if the original one already diverged at the endpoints, and you differentiate, it's definitely going to diverge. Okay, you can only gain in integration and lose in differentiation. That's the... Okay, good. Let's do... So we're accumulating... What we're doing is accumulating methods of finding... And you need to practice this a lot. You're going to practice this in homework and in tutorials. You need to practice this, how to find series from given series. I have some more examples, but before them, I want to resolve one little issue that we discussed earlier, which is how can we guarantee? In everything we did, we still had no guarantee that the power series really converges to the function. And we had an example that in some cases you can get a power series, a Taylor series, and it won't converge to the function. So here's the statement. So the question we're trying to answer is, when does sigma an x to the power n converge? So when is it true that this thing converges to the function it was obtained from? Okay? You start with a function. It has infinitely many derivatives. That's a necessary condition. You can write its Taylor series. When is it true that this thing converges to the function? Okay. So the claim is that this is true if and only if, and all this discussion is in the interval minus RR, in the domain of convergence, in some domain inside the radius of convergence. Okay, so it's going to converge to something, but does it converge to F? Okay, so the claim is that this converges to F if and only if Sn, I'm going to change something here. I'm going to call this, okay, let's not change it. And let's call this capital N. Sn of x converges to f of x as n goes to infinity. What is Sn of x? Those are the partial sums. Saying, and this has to be true for any x inside this minus RR interval. And this is a capital N. So this Sn of x is the sum from 0, not to infinity, but only to capital N of an x to the n. That's how we defined series. For a fixed x, the series is defined as the limit as n goes to infinity of the partial sums. Do you agree? So if for any x this thing converges to f, that means that the series converges to f. Do you agree?
So the remainder gets smaller each time.
Wait. You're again a step ahead of me. Do you agree to this? Okay. This is if and only if, saying that Sn of x, the partial sums, this is a capital N, right? Saying that these converge to f is the same as saying Sn minus f converges to 0. Do you agree to this? For any x. But what is this difference? What is Sn of x? What is the sum only up to n?
Is it Tn?
It's the Taylor polynomial of degree n, right? The partial sum, the sum of the first only n powers, is precisely the polynomial of degree n. I should have called it maybe Pn or Tn or whatever. Do you agree? And what's the difference between the polynomial and the function? That's the remainder. So this happens if and only if the remainder, Rn, but Rn of x, for every x, goes to 0. For every x here.
Why it's going 0? It has to be just less than that.
This is equal to this. The difference between the function and the polynomial is the remainder. That's the definition of the remainder. The remainder from the good old discussion of Taylor polynomials. So if the remainder becomes smaller and smaller and smaller as the degree gets bigger and bigger and bigger, then the series is going to converge to the function. And we had a sufficient condition for when this happens. And I'm going to remind you of that. Right, that the derivatives are uniformly bounded, that there's a common bound for all the derivatives. So let me remind you of that. And that's going to be the sufficient condition guaranteeing this phenomena. So let me write that. And we wrote it before when we discussed Taylor polynomials, and we were interested in the question, when does taking higher and higher degrees improve our approximation? So it's exactly the same answer. And the answer is, so let's write it as a theorem. If f is differentiable infinitely many times, so that was a necessary condition, I have to still include it, on some interval, and you need it to be a closed interval in this theorem, on some interval, and there exists some m such that the nth derivative of f at x in absolute value is less than or equal to m for all x's in this interval and for all n's. So that's this uniform bound that then captures all the derivatives on all the interval simultaneously. Then Rn goes to 0. And if Rn goes to 0, by the previous discussion, the Taylor series converges to the function. And we even verified this condition for e to the x, for sine of x, and you can think of it for other. By the way, proving this is not too hard. What comes in there is it makes the use of Lagrange's theorem. Lagrange's theorem just pops up everywhere, and there's a little sandwich argument, and it's not a hard proof. Okay. So, yeah, questions?
How do we apply that? If I look at this, like
We did it. We did examples. We discussed that this is true for sine x. We discussed that this is true for e to the x. We discussed that this is true for cosine x. We did it when we discussed Taylor polynomials. This is not the first time you're seeing this theorem.
for me it feels like.
Well, since this is recorded, I'm willing to bet. I have proof. We did it. We discussed this when we discussed Taylor polynomials. Okay? So I don't want to do examples again, because they were there. You can look back and see. Okay? More questions? Yes?
Seems like e to the 1 minus 1 to the... Yeah. The example that we used, that it doesn't converge.
Mm-hmm.
Doesn't that fit this?
Evidently not. So the example of the function whose Taylor series does not converge to the function, that e to the minus 1 over x squared, apparently doesn't satisfy this. Okay? It's not the derivatives at a point. The derivatives at 0 were all 0. Then that was easy. But you need to take the formulas for the derivatives on some interval, and those were pretty complicated if you did all the details, and they don't satisfy this. How do I know with such certainty? Because if they were to satisfy this, then that function wouldn't be a counterexample. Okay? But there's work in there. If you didn't do that example, it's not too late. Do it. It's very important. It's a very important example. Okay. So this resolves the issue of when does the Taylor series actually converge to the function you started with. Okay? So the last theorem I want to mention now, again going back to the tools for finding power series, and this is a vast topic. Okay, we're really not exhausting it, and there's a lot of things that we're not saying. Like in many things in this course, this is a first course. This is many things are introductory. So here's another theorem. So suppose sigma an x to the n converges to f of x, and sigma, we need two of them here, bn x to the n converges to g of x. When I write equals, I mean that there is some radius of convergence, positive radius of convergence, and that this equals mean that this series actually converges to the function. Okay, it's not just the Taylor series, it's the Taylor series, and it satisfies that it actually converges to the function. Then, so 1, sum c, where c is some constant, an x to the n, equals c f of x. You can stick in a constant, a scalar, and still maintain that convergence, and the limit is going to be c times the function, and it's going to be precisely the same domain of convergence. I'm a bit short on time, so I'm skipping the precise details about the domains. Sigma an plus or minus bn x to the n converges to f plus or minus g. Three. What about f times g?
Non-zero.
What about f times g? Is it true that sigma an bn x to the n converges to f times g?
Yes.
So the answer is that would be not reasonable. Okay? Let's do a little side calculation here and try to decipher what I want to write here. Okay? So what is this an x to the n? It's a0 plus a1x plus a2x squared plus ... And f times g has to equal the product of this times b0 plus b1x plus b2x squared plus ... This is going to equal f times g, right? How do we multiply two things like this? The product of these is not a0 b0 plus a1 b1x plus a2 b2x squared. That's not how we multiply things like this, right? How do we multiply them?
Distributive.
Right, somebody's doing this here. And that's true. There's billions of multiplications going on here, right? We have to multiply a0 by every one of these and a1 by every one of these. And the powers get all messed up. Do you see that? Okay? So if you decipher this, what is going to be the free coefficient in the product? A naught, B naught. That's the only way we can get something without x's. Do you agree? What's going to be the coefficient of x? Just x. It's going to be A naught B1 plus A1 B naught. Do you agree? And so on. For x squared, you're going to get A0 B2 plus A1 B1 plus A2 B0. Do you see that? And so on. So this is the explanation from what I'm going to write here. Define Cn to be the sum, the finite sum, k equals 0 to n of ak, b, n minus k. This is going to give you precisely these interchanging all possibilities. Then, these are the coefficients for then sigma Cn x to the n, and this is the infinite sum, equals f of x times g of x. Okay? And by the way, this is going to be, the domain of convergence here is going to be the intersection of the domains of convergence of the two original functions. So the smaller of the domains of convergence. Okay, so I'm not even going to write it, but there's also a way of writing down the power series for, or it's not a closed formula, you have to think about it a bit, but it's a technique of finding the coefficients for the quotient. And moreover, there's a way of writing the coefficients for the composition. That's even more tricky. So I'm not going to write those. I'm not going to ask you about those because there are 5 minutes left to the course. But just know that they exist as well. I just want to do one example, and that's going to be the last example for today and the last example for this course. So here's really a last example. So suppose, I don't even remember what number it is. Last. Oh, so that one last. Example infinity, right? We finally get there. So suppose that you get the function f of x equals 1 over x squared plus 2x minus 3. And you want to find the power series corresponding to this function. So how do I approach this? I try to think, there's these 4 ones that I know. There they are. Does it resemble them? Does that thing look like ln of 1 plus x? Not really, right? Yeah. Does it look like sine of x? No, it's just what? It's a rational function, right? It's 1 over a polynomial of degree 2. Does it look like e to the x? No. Does it look like this? Well, do you agree that it's the closest to this, maybe? How do I get it to be like this? Very good. Do partial fractions. Okay, so again, a tool from the past pops up, but you have these tools. Use them. Very good. So we'll do partial fractions to this, so let's do it. So I'm going to skip the intermediate calculations, so just partial fractions. I'm assuming you all know how to do this very well. So what I get is 1/4 1 over x minus 1 minus 1 over x plus 3. Now these two look significantly closer to the geometric one, right? To 1 over 1 minus x. I still have to play with them around a bit. I still have to modify them to have them look exactly the way I want. And the way to do it is, I'm going to leave this 1/4 outside. This one I'm going to write as minus 1 over 1 minus x. Do you agree? And this is precisely the geometric one now. And this one, there's this 3 here. The geometric, it has to be a 1, and it has to be a minus. So I pull out a 1/3 and a minus. So I get minus 1/3, and then I can write it as 1 over 1 plus x over 3. I didn't pull out the minus. It's still this minus. Sorry. I just pulled out a 1/3. Do you agree? Okay. So what did I get? This one is precisely the geometric one. This is sigma x to the n with no additional changes. Do you agree? What about this one? This would be sigma x to the n, but when I'm plugging in, instead of x, minus x over 3. Do you see that? So this thing is, this one is sigma, not x to the n, but minus x over 3 to the n. Do you agree? Okay, so it's not too hard. You just have to, you need to do some of these to get used to it, to not be scared from them. That's. Well, you'd have a negative on this 1 here as well, and that would not be good. So what do I get? So all in all, I get minus 1/4. And now I can write, instead of this thing, I can write minus sum n equals 0 to infinity x to the n. That's the first one. And then minus 1/3 sum, 1 second, n equals 0 to infinity. And then I have this thing. So it's minus 1 to the power n, 1 over 3 to the n, x to the n.
The first one should be plus.
Oh, I pulled out a... yeah, right, you're right. If I pull out the one... yeah, no minus out here. Let's leave it like this. There's one more step to do. Sorry. So what's the last step? I need to add these two series, right? This is now written as a sum of two series. How do I add series? With that theorem. This is a series for f, this is a series for g. For f plus g, I just need to add them up, but I have to do it carefully. So so this minus can come out. I really don't want to erase. So let me continue here. I want you to have it visible in one frame. So this equals, let's pull out the minus here. So now there's the minus 1/4. And then there's going to be one sigma, n equals 0 to infinity, x, more space, x to the n. And what's the coefficient of x to the n going to be? From here, this contributes a 1. That's the an. And this one, let's see. This 1/3, I can throw inside the sigma. That's a constant. I can throw it inside and get an n plus 1 here. Do you see that? So I'll have a plus negative 1 to the n over 3 to the n plus 1. And this is the power series for this function.
Can you explain that?
Good. What about domain of convergence, very quickly? The domain of convergence for this one was x in absolute value less than 1. Do you agree? The domain of convergence for this one was x over 3 in absolute value less than 1, which means x less than 3. Do you see that? So for both of them, this requires x to be less than 3. This requires x to be less than 1. So for everything to work, I need the smaller. So this is true for x less than 1. Good?
Did you say something funny when you add from multiplying?
Yeah. Okay. So there are many, many more examples you can do, but we're gonna stop here. I wanna just make one comment about power series. One last comment about power series. When you want to do approximations, that's not the tool you want to use. You want to use the Taylor polynomial. Okay? The power series tells you this function equals this series, equals. No remainder, equals this series, providing x is less than 1. But this is an infinite sum. It's not going to help you in calculations. Okay? If you want to say, to get an approximation for this function, then stop at n equals 4. Then you get the polynomial plus a remainder, and if you can control for the remainder, then you know a good approximation. That's what we discussed when we discussed Taylor polynomials. Okay? So this whole business of power series is a way of working with functions, with equal, not with approximations, but it's not going to help you on the approximation side. For that you need the first discussion of this theory, which is the Taylor polynomials. Okay? We are not covering the general theory of function series, where you can have sum, and instead of x to the n, you can have for n equals 1, you can have sine x. For n equals 2, you can have cosine x. For n equals 3, you can have x to the power 14. For n equals 4, you can have e to the x. Those things also exist, and depending on where you continue, you will encounter more series of functions in a more general context, like Fourier series and whatnot. We're not going to cover them in this course, just a question of the scope of the course and the time we have. So it has been a pleasure to teach you, really, and I want to wish you a lot of success on the final exam. And I guess we stop here.